This video is a review of definitions of acids and bases. You should already be able to identify acids and bases, name them, and describe the pH scale, but by the end of this video, you should also be able to classify acids and bases based on two theories, identify conjugate acid bases, identify strong acids and bases, and explain and write acid-base reactions. So the question in the video is, are the following acidic, basic, or neutral? So we have pseudoephedrine, which is Sudafed, the type of medicine you might take if you're congested and your nose is all clogged. Quinine, which is treating malaria, and nicotine, the bad stuff inside vape pens and cigarettes. So in order to answer that question, let's go through some basic chemistry. An acid is a substance that when dissolved in water increases the concentration of hydrogen ions as pH is less than 7. Some examples are aspirin and lemon. A base is a substance that when dissolved in water increases the concentration of hydroxide ions. That's really important that you know the difference between hydrogen, which is H+, and hydroxide, which is just OH-, and its pH is more than 7, something like Tums or ammonia. And there's a second theory, the Bronsted-Lowry theory, that we used last year. We remember it as bases accept, acids donate, the bad theory. So acids are proton donors, and the protons refer to hydrogen ions again. So both Bronsted and Arrhenius theories think that acids have had to have those hydrogens in the front of their compound. And that bases, for the previous theory, have hydroxides. In this theory, they don't have to. They can just gain this hydrogen ion or this proton. The reason we call it a proton is because the hydrogen regular has a proton in the center, an electron in the first level. When you talk about hydrogen ions, it loses its electron. So it's literally just a proton that's left in that atom. And so therefore they're synonymous, H+ and proton plus, right? Some things can be either acid or base, amphiprotic. So you'll notice that I'm giving you some subliminal messaging. The red is always referring to acids because in litmus, acids turn litmus red. And the blue is referring to the bases because they turn litmus blue. And so these examples are amphiprotic because they have a hydrogen in the front of the compound that they're willing to lose, but they also have a negative charge that they're willing to gain an H+. And the exception to that only rule is water. We have to know that water can do both as well. It can gain an H+ and become H3O+, which is not as intuitive as the previous two that would gain H+ is. And it could also lose its hydrogen in the front. So these all have hydrogen ions that you could donate and a negative charge, except for water. You just need to know. What happens when the acid dissolves in water? So water acts like a Bronsted-Lowry base and abstracts a proton from the acid. So if you look at the acid and the water, the hydrogen is taken off of the chlorine. Chlorine's now alone as a negative charge. Because the hydrogen was positive, it goes onto the water and makes H3O+. So you have the same charges to beginning and end, 0 and 0. It's just that they're separated now. The H got migrated over to the water. As a result, the conjugate base of the acid is a hydronium ion is formed. So notice that there's something called a conjugate, whatever it turns into. Like when you conjugate a verb in a Spanish or foreign language class, it looks like the same root, it just has a different suffix. The same thing's going on here. This is the same chlorine, it just doesn't have the hydrogen. This is the same particle, it just has a hydrogen. So HCl conjugates to chloride, and water conjugates to H3O+. It also changes what kind of substance it is since it gains or lost its hydrogen. So to make sure it's clear, an acid will remove its hydrogen and become a conjugate base. A base will gain its hydrogen and become a conjugate acid. It changes into the other type of substance. So reactions between acids and bases will always yield conjugate acids or bases or salt and water, as we saw previous in the year. So the strength of the acid depends on how well it dissociates or breaks down in water. The better it dissociates, the more ions it has, the better electrolyte it is, the better it conducts electricity, lights a light bulb, for example, and therefore we say it's a strong conductor and therefore a strong acid. If it doesn't conduct, it's a weak acid, similarly with bases. So strong acids will completely dissociate in water, and therefore their conjugate bases are quite weak. The base won't lose its hydrogen or anything like that. It will gain its hydrogen back. It will just stay that conjugate base. Weak acids only dissociate partially in water. So for every 100 acids, maybe only 5 of them actually break up, and it will maybe conduct a little bit of electricity, but really, for the most part, you won't see much of a difference. And their conjugate bases are also probably weak bases. So finding a conjugate acid is not that bad. What you have here are bases, or maybe amphiprotic things. And if it becomes an acid, it has to have more hydrogens than it started with. So to gain a hydrogen ion, NH3 becomes NH4+. Notice the charge. HS minus becomes H2S. HSO4 minus becomes H2SO4. H2PO4 minus becomes H3PO4. So notice that their conjugate acids always have more and more hydrogen ion that makes it more acidic, and the charge goes up. If you're finding a conjugate base, that means that we have to have less hydrogens. So these are all acids because they have hydrogen in front. We're going to take that hydrogen off, but remember you're also removing a plus. So they become ClO4 minus, or Cl minus, or H, just one H comes off, so HSO4 minus, or H2PO4 minus. So for now, just keep in mind that only one hydrogen is being removed, and we'll show later in the topics why that's going to happen. But for now, only one hydrogen per molecule to become the conjugate base. Neutralization occurs when you have the acid and the base come together that have some completely different properties to form a salt and water. An example would be hydrochloric acid that had a hydrogen in the front, and sodium hydroxide that had hydroxide in the back. They double replace. The sodium chloride is a salt, it's neutral now, and the water is left over from the H in the acid and the OH in the base. And now what you used to have at a low pH and a high pH now equalizes to 7. Or when you had very acidically bitter, acidic tasting or sour tasting substances with very bitter tasting or soapy tasting bases, now they have just salty tastes. So they lose their properties. When the substance is neutralized, they lose their properties and the pH will equal to 7. Here's just another example of that. The HBr is an acid, the BOH2 is a base. It doesn't matter that there's two of them. What that means is they'll both dissociate, it'll form water, and then you'll form barium bromide. And the reason why I know it's BaBr2 is barium's +2 and bromine's -1. Now you might say, this doesn't make sense to me. All you would need to do to make this make more sense is to put a 2 in front of HBr, because for every 2 hydrogens there needs to be neutralizing with 2 hydroxides, and that would balance the equation. So what I would recommend doing is writing your equation out and balancing it at the end. Acids also react with most metals. So one hydrogen ion will be replaced with the more active metals. The inactive metals you need to know are copper, silver, and gold. Things that we make jewelry out of tend to not react with metals. So if you look at the picture, the strong acid will bubble a lot with magnesium, switching out the hydrogen for the magnesium in the acid, and the hydrogens come off. A weak acid will do it, it just won't do it as often. And that's why we call it weak, because it doesn't seem to be changing as much. So here's what the reaction looks like. The two HCl's reacting with magnesium. Notice the magnesium switches with the hydrogen, becomes MgCl2. Hydrogens are never alone, they're diatomic, and therefore we put a 2 in front of HCl to balance it. This also could happen with zinc, and you can see how the reactions are really similar. You will not see this happening with copper, silver, and gold. So back to the question of the video, are the following acidic, basic, or neutral based on what you've seen in the pictures or given? So the Sudafed is basic because it has that hydroxyl group. The quinine is also basic because if you look through, it has a hydroxyl group. OH is really pretty clear for that. And then for the nicotine, the only indication we have for this is the pH is 3, so that means it's acidic. So you could use multiple things to look up if it's acidic or basic. At this point, you should be able to classify acids and bases based on the two theories, Arrhenius and Bronsted-Lowry, which is a bad theory. Identify conjugate acids and bases and switch the H's around. Identify strong acids and bases, making sure that they know that they react more and they have more ions if they're strong. And explain and write acid-base reactions.